Students, it's time for something very important. Poor Peter Gibbons in that clip. He just wanted to get to work on time. Couldn't figure out when to change lanes. Here's a question. When should you change lanes? At what point should you change lanes? Obviously, he picked the worst times. Whenever he changed lanes on the highway, traffic in that lane started to slow down. Now, of course, this is a difficult problem because you don't know which lane's going to be faster at which time, and you can only predict. And, of course, you have to make a commitment to one lane or the other before you learn whether it's going to be a fast lane or a slow lane. But let's imagine a scenario in which you actually knew in advance how the lane traffic was going to go. Let's say I told you that for 1 minute, the left lane was going to go quickly, and for the next minute, the right lane was going to go quickly. If you knew these things in advance, how do you pick the optimal time to switch lanes? It's a good question, and let's think about that. So here's a hypothetical driving situation. We have two lanes. You have a starting point, and you have an ending point. Let's say you have to get off the highway at the ending point. The edges, the blue edges here, we've written, those are have some labels attached to them, some weights. So let's just say that every weight written in red is just the time it takes to do that transition. And let's just say you know in advance that it takes 15 seconds to change lanes. Now, to go forward in each of the lanes, rather than changing lanes, if you want to go forward, takes some variable amount of time. Let's say if you're in the right lane, initially it takes 4 seconds to go to the next step. But then it takes 25 seconds, and again 25 seconds with the last step. It takes 4 seconds. So the question is, what is the shortest way to get from the start to the end? If you knew in advance what the traffic was going to be like, how would you compute the optimal path here? And it turns out we can do that using what's called dynamic programming. You may have seen a version of this in what's called Dijkstra's algorithm, which is another shortest path algorithm. But let's try to do this using dynamic programming, which is going to be the focus of the next segment of the course. So what I'm going to write now is in green. It's going to be the quickest time it takes me to get to various nodes. You're going to notice that I have to start at the beginning. It takes me 0 seconds to get to the first node because I'm starting there. To get to this node, well, the only way I get to this node is by taking this one path. That's going to take me 15 seconds. Similarly for this node, to get to this node is going to take me 4 seconds from the beginning. Now we get to our first interesting case, which is how much does it take, how long does it take to get to this top node right here? Well, we could either have spent 15 seconds getting to this node and then spent another 10 seconds getting to this node, that's 25 seconds, or we could have spent 4 seconds getting to this node and then 15 seconds getting to that node, which means that that's only 19 seconds. 19 is better than 25, so I'm going to write down, 19 here. So I'm going to write down 19 here. Okay, so for this guy, we could have spent either 19 seconds getting to this top node, then change lanes, spent 15 seconds changing. That would have given us a total of 15 plus 19 is 34. Or we could have gotten to this bottom node here, spent 4 seconds getting there, and 25 seconds moving over. That's 29. 29 is actually better. So I'm going to write 29 here. It takes 29 seconds to actually get to this bottom node. That's the shortest path. Now again, how do we get up to this node above? Well, we could have either taken the 19 route, we could have gotten here and then moved over, that would have been 29, or we could have gotten to this bottom node and then that would have taken 29, also plus 15 to change lanes. Obviously, the 29 plus 15 is worse than 29, so I can write 29 here, right? Again, for this node down here, how am I gonna figure out what to do here? Well, I could have either spent 29 seconds getting to this node and then 25 crossing over. That's a total of 54. Or I could have gone up to this node over here, spent 29 seconds getting to that node, and then 15 going down, changing lanes. So that's gonna be smaller, which is 44. Okay, so now how about this last top one here? I could either have gotten up to this top node here. That would have taken 29 seconds, and then it's 20 seconds to cross over. That's 49 seconds. Or I could have gotten down here and moved up, and that would have been 44 seconds plus 15. That's going to be a total of 59 seconds. So clearly this is preferable. I can get here in 49 seconds. And again, let's finish this off. We now have the last node to get to the end. What's the optimal way to get from to this spot right here? Well, it's pretty clear that 49 plus 15 is larger than 44 plus 4. So really, I would have wanted to have taken this bottom path here and just paid 4 at the end. So this is going to be a total of 48, right? 48 because 44 plus 4 is lower than 49 plus 15. And if you look at this, you can sort of figure out what the optimal path is. We just have these numbers written down, which you got from our dynamic programming solution. Let's actually figure out what the best path is. Getting from here, I should have taken this route. Okay, what was the best way to get here? That was to do this node right here, right? That was optimal. Now, how do I get from this to this where it's marked 29? Right, I went along this path right here. And how did I get to the 19? I guess I got to the 19 by doing 4 plus 15, so I went down that way. And then, of course, how did I get here? There's only one way. I went this way. So here is the optimal sequence of lane changes if you knew how long it was going to take to get from these various nodes. And there we have the optimal solution. And this is basically using dynamic programming. So let's just take any DAG, any directed acyclic graph. Here's one with 6 nodes. So the starting node is right here. Right, this is the starting node. Now we want to ask, how long does it take us to get from this starting node to all other nodes in the graph? The first thing you have to do is to topologically sort this graph. So below here we have a topologically sorted version of the graph. And it's helpful to work with the topologically sorted version. Oh, what is it? So what is a topologically sorted version? It means that all of the edges always point forward. You can always order a DAG in a way such that all of the edges point forward. There's no edges pointing backwards. So what you're going to do here is you're going to iteratively find the shortest path from the start node to all other nodes. Right, this is the start node. First you move over to this node 3, and you ask yourself, what's the shortest distance from this node 3 to the starting node? And it turns out you have to follow this one edge, right? So now when we want to compute how far is it to get from this second node, right, you have two options. You can either have gone through this node, or you could have taken this path, right? Well, this thing had a distance of 2, right? You had to take that edge 2, pay 2 there, and then pay 4. That would have been 6. But it turns out if you'd just gone directly, you would have gotten 2, right? And we can keep iterating through this process. Here, the optimal path is going to be 8 because there's only one way to get here, right? We prefer this path right here. For this one, we could pay 8 and then 1. That would be 9, but actually it's preferable to pay 2 and then 3, so this is 5. And then to get to this final node right here, we would rather pay, we could do 8 plus 1, right? We could have started from here and then moved down this thing, but actually it's preferable for us to pay 5 and then 1, right? 5 to get to this node 4, plus 1, and the answer is 6, right? And now we found the shortest distance to all nodes in this graph. So here I've highlighted what the algorithm is. You can just initialize all the distances to infinity, just initialize it to some basically maximum value. You write the distance to the source node is 0. That's getting from the source node to the source node takes no time at all. And then for each graph, or each node in this graph, in the topologically sorted order that we've created, we just do the following. We said that the distance to node V is the minimum of the distance to u for all nodes u that point to v, plus whatever the edge weight is of uv, right? This L of uv are these values. This is the L of uv values right here, right? So you pay whatever it took to get to the node behind you, plus whatever the cost of that edge is. And this is it. This is this little, this algorithm works, and it will compute the shortest distance from the source node to all nodes in the graph in this iterative fashion.